Now let us see the next method, which is from hydrocarbons. In this we will see that yes, from hydrocarbons like from alkenes we can prepare by ozonolysis. So by ozonolysis of alkenes. This is again is a reaction which we have already done in class 11th. What we do is when any alkene like this one, I have already taken an unsymmetrical alkene to make it very clear which part gets converted to which one. What we can do is when we treat this with ozone, we know that ozonolysis takes place and we get ozonide like this. This is called ozonide. Now this ozonide on reaction with zinc water breaks it like this. So what we get is an aldehyde of this group and aldehyde of this group. So we get this one CH3CH2CHO plus CH3. So it will be formaldehyde, sorry, it will be HCHO. So this is how we can get aldehydes as well as ketones, because see, if the double bonded carbons are having only one chain, that carbon gets converted into an aldehyde. If that is having what, two carbon chains, it will be getting converted into a ketone. Let me give you an example of that also. If we are having, suppose, an alkene like this, we know on ozonolysis it is going to form an ozonide which will be like this. This on reaction with zinc water will be forming what? This part will form ketone, because this particular carbon which I am circling is having two alkyl groups. So that gets converted into a ketone, and this one becomes your aldehyde because that's having only one carbon chain. So that is how we can have aldehydes and ketones prepared from alkenes. The second method under the same heading from hydrocarbons is by hydration of alkynes. See, we know if we have acetylene like this one, acetylene, and if we put water in presence of H2SO4 and mercury sulfate, what we get is, of course, its addition takes place like this. This molecule shows tautomerism. So what happens is it gets converted into an aldehyde ethanol. So this is how the addition of water, which is called hydration in acidic medium in presence of mercury sulfate, converts it into an enol, which gets tautomerized to give you an aldehyde. If we have a 3-carbon alkyne, like let me give you an example of this one. If we have propine, the addition of water, of course, along with in presence of sulfuric acid and mercury sulfate, follows Marconikov's rule. So addition takes place as per Marconikov's rule, but this molecule again will show tautomerism, and what we will get is propanone. So higher alkynes gives you ketones and the acetylene gives you an aldehyde, ethanol. So this is how we can also prepare aldehydes and ketones from the hydration of alkynes. The next method to prepare aldehydes is from acyl chlorides, and it's a name reaction called Rosenmann's reduction. See, it's an exclusive method of preparing aldehydes where acyl chlorides are partially hydrolyzed or reduced to the corresponding aldehydes. So what we do is, in this cases, if we have an acyl chloride like this, we hydrogenate this in presence of palladium, barium sulfate, and it gets reduced to what your RC double bond OH plus HCl. Now it's a partial reduction. Why I am saying so? Because if this barium sulfate is not used here, then the aldehyde form would have been reduced to the corresponding primary alcohol. So in order to prevent this, we have used the barium sulfate, and that is why this barium sulfate is called poisonating agent. Now this reaction is applicable both for aliphatic and aromatic aldehyde acyl chlorides. So if we have this one, it's called acetyl chloride. This on reaction with hydrogen, palladium, barium sulfate is going to give us ethanol or acetaldehyde. And if we are having this compound called benzoyl chloride, this on reaction with hydrogen, palladium, barium sulfate is going to give us what? Benzyl dehyde. So this is how we can easily prepare aldehydes, and that is why this reaction is called exclusive method of preparing aldehydes. The next reaction is from nitriles and esters. Yes, this is again one of the reduction methods, and the cyanides and the esters can be reduced to their corresponding aldehydes. Now, what is most important to notice that if we are using cyanides and we are reducing them, the reaction is called Stefan's reduction. Now let's talk about first the Stefan's reduction. When any alkyl cyanide in this is reacted with SnHCl or FeHCl, so it's a reduction in acidic medium, that leads to the formation of what? Imine. So imines are formed, which gets what? Hydrolyzed in acidic medium like this, they break it like this to give corresponding aldehyde and ammonia. See, it's a partial reduction. The cyanide is not correspondingly, doesn't get reduced completely to the corresponding primary amines. It's stopped in between. It's only getting converted into what? Imines. Only one triple bond, one pi bond is removed by the addition of 1 mole of hydrogen, and the second one remains as such. That is why this on hydrolysis gives us aldehyde. That's called Stefan's reduction. Now we can take the example to find out how we can write this reaction as such. If we have CH3 CH2 C triple bond N, it's called propane nitrile. That's why this on reaction with SnHCl followed by hydrolysis in acidic medium is going to give us the same carbon aldehyde propanol plus ammonia. So this is how this reaction takes place. Now, in place of using this acidic medium reduction SnHCl or FeHCl and then convert, what we have developed another very important reducing agent which is called dibyl H. So we are using nowadays an alternate reducing agent that's called dibyl H. What is this dibyl H? This is diisobutyl aluminium hydride. This compound it is this and this. Since in this there is only one aluminium hydrogen bond, it will always lead to what? Partial reduction. So there is no fear of getting the further amines getting reduced to the further amines, primary amines. That is why this dibyl H always gives us what? The amines. So obviously the yield is much better, and what we do is, if we take any particular cyanide, like we have taken ethane nitrile, or it's also called acetonitrile, with dibyl H, and then we do, because this is going to give us amines, and then we will be like, let me write down like this, CH3 CH double bond NH, and this on hydrolysis in acidic medium will give us ethanol or acetaldehyde plus ammonia. So same thing. So in place of SnHCl we are using dibyl H. The most important thing about this dibyl H is this, that this dibyl H can reduce the esters, yes, esters to the corresponding alcohols also. In the esters, what happens is the acidic part gets reduced to the corresponding aldehyde. Let me give you an example. Suppose we have this ester, this is called methyl propanoate. This on reaction with diol H will convert this acidic part into the corresponding aldehyde CH3CHO. So what we get is propanol plus we get, of course, in this case the methanol which is left out, and alcohol is given out. So the acidic part of the ester easily gets converted into an aldehyde, and this is what is the use of the diol H's. Let us see the preparation methods of aromatic aldehydes. The first in this category is from methyl benzene. Yes, methyl benzenes can be converted to the corresponding aromatic aldehydes by two methods. The first one in this is called Etard reaction. Yes, it's a name reaction in which what we do is toluene is reacted with chromyl chloride gas in non-polar medium like CS2 or CCl4. Now this converts toluene into a chromium complex like this one. We call this as chromium complex. This on hydrolysis gives us benzaldehyde. So it's the oxidation, it's not the direct oxidation. What is happening is a complex intermediate is formed which cannot be further oxidized, and that on hydrolysis is giving us aldehyde. See, the problem with the aromatic alkyl benzenes is this, that they, once we are trying to oxidize them, they actually get directly oxidized to benzoic acid. So we cannot let their oxidation go on its own, because that is going to give us the acid group. So we need to stop it in between. So that is why we need to use the reagents which convert them into one of the complexes and stops their further oxidation, which on hydrolysis gives us aldehyde. And Etard is a very good method because by using chromyl chloride gas. The second is by using the chromic oxide. The second in the category is by using chromium oxide. Now in this what we do is toluene is reacted with chromic oxide or chromic anhydride in presence of acetic anhydride. This converts this toluene into we call it benzylidene diacetate, which on hydrolysis and heating gives us benzaldehyde. This is again a method in which direct oxidation is prevented by forming an intermediate which is not getting further oxidized, and that gets converted into a benzaldehyde. So by using chromic oxide in acetic anhydride, we can oxidize toluene to benzaldehyde or methyl benzene to this compound which is called benzaldehyde. The third method to prepare benzaldehyde from the same methyl benzene is by side chain chlorination. Yes, we can do the side chain chlorination followed by its oxidation. So what we do in this case is we take toluene, we do its chlorination in UV light. What we get is CHCl2, and then we will do its hydrolysis at around 373 Kelvin, which is going to give us what? 2 OH groups on the same carbon like this. So this is an intermediate which is going to give us, with the loss of 1 water, benzaldehyde. So toluene by side chain chlorination can also give us benzaldehyde. There is one more method of preparing benzaldehyde, and that is called Gattermann's Koch reaction. Yes, it's a method of preparing benzaldehyde directly from benzene by using carbon monoxide HCl in presence of anhydrous aluminium chloride, or we can take cuprous chloride. It's an example of electrophilic substitution in which what we get is benzaldehyde and HCl. So this is called Gattermann's Koch reaction. Now let us see the methods of preparation of ketones, which are the exclusive methods of preparing ketones. The first one in the list is by using acyl chlorides. In this, what we do is, it is by the action of dialkyl cadmium, R2CD, dialkyl cadmium. First you need to know what exactly this how we get this dialkyl cadmium. See, it's an organometallic compound, like we have used Grignard reagent. So what we do in this is, how we get this one is, you can take any Grignard reagent and you can react this with cadmium chloride. What you get is dialkyl cadmium plus MgXCl. This is how we can get dialkyl cadmium. Now what we can do is, we can take any acyl, let's take this R as R dash, so that we are having R dash. So if we are taking any acyl chloride and we react them with dialkyl cadmium, what happens is, the 2 molecules of this will react, this R dash will substitute this chlorine. So what we will get is this ketone and cadmium dichloride back. So that is how this is a very exclusive method of preparing the ketones, only ketones. See, we have seen Rosenmann, it was from acyl chlorides, but that was only giving us what? By reduction, partial reduction, aldehydes. And we are using now again the acyl chlorides, but by the action of dialkyl cadmium, we'll be getting only ketones, and that too of our choice, because this R can be arranged by us and we can take any this R dash group. Let us take an example, like if we want to prepare, like let us take example that we wanted to prepare 2-pentanone, and we are taking acetyl chloride. Now for taking 2-pentanone, we need to have 3 more carbon here. So what we will do is, we will take the dipropyl cadmium as the compound along with the cadmium chain. So we will, when we will treat this one with this acetyl chloride, what we will get is this compound, CH2, CH2, CH3 plus cadmium chloride. So we get pentane 2-on. So this is how we can prepare ketones of our own choice. The second method to prepare exclusively the ketones is by the action of Grignard's reagent on cyanides or nitriles. See, if we take any alkyl cyanide and if we take any RMgX, we know that this is going to show us a nucleophilic addition reaction like this, which will shift up by pi bond on nitrogen, which will require a negative charge, which will attract magnesium. So we will having R, C, R dash, double bond N, Mg, Br. So this is the adduct which is formed. This now on hydrolysis in what acidic medium will give us compound like this. So the compound which we get will be a ketone and magnesium amino bromide. So this is how we get a ketone, exclusively a ketone. So alkyl cyanides gives us ketone. This is, we have alkyl cyanide, it's a common nomenclature of the nitriles. Let me give you an example for this. Like suppose we have acetonitrile or ethane nitrile, and we have reacted this with ethyl magnesium bromide. This will attack here, this will shift here, this will make this nitrogen to attract this one here. So what we will get is this CH2, CH3 double bond N, Mg, Br. This is the adduct formed, which on hydrolysis in acidic medium is going to give us compound like this. So we get what butanone, 2-butanone plus magnesium amino bromide. So this is how we can prepare ketones from the nitriles. And let us see the third method to prepare ketones exclusively, which is by Friedel-Crafts acylation. We know benzene or the substituted benzenes on reaction with any acyl chloride in presence of anhydrous aluminium chloride shows electrophilic substitution reaction, and what we get in this is these ketones plus HCl. So the compound formed is acetophenone, or it's called phenyl ethanol. So by simple electrophilic substitution on benzene or its substituted benzene, we can get aromatic what ketones.